video, I'm going to be going through method of joints for exercise 1.2 in the Engineering Studies, the Definitive Guide, Volume 2, second edition. Now, what we're going to do is we're going to be using method of joints. Where do we use method of joints? Well, if you like me and Snoop Dogg, we like the method of joints. I think it's actually a good method, but we don't teach it because it's harder for high school students and it's less relevant for high school students. Why is it less relevant? Because high school students rarely have to solve an entire truss. They usually have to solve one or two pieces. Usually we give them the middle ones anyway, so that really encourages them to use method of sections. Method of sections only builds on what you already know about using moments, so a lot of the time that makes it easier. But the method of joints has a couple of opportunities. One is, it is particularly good if you're solving corners. It's good if you like geometry rather than algebra, and it's good if you have to solve the whole truss. That's where its real benefits are. So what I have here is I have this magnifying glass that I thought would be a clever prop, but I think it doesn't show up very well on the camera, but too bad. What I'm doing is I'm going to zoom in on reaction R. Originally I was going to start on zooming in on reaction L, this location L, but I realized that I didn't like that because this one's a little bit more complicated. It's got a diagonal force, so we're going to start with the roller first. Now I've already solved these here, and I'm going to go through how I worked that out. So that number there is wrong. There we go. I'm going to show how we're going to work that one out. Okay, so what we've got here is, what have we got? The concept of method of joints. We know that if we cut through any section, the forces have to be balanced, otherwise the whole thing falls apart, right? So we talk about like vector stealing just half of the bridge. If we cut through any point, it has to be balanced left and right, otherwise the whole thing explodes. I find it actually much easier to understand that the method of joints, if we don't have equilibrium in each joint, the joint will just pull apart. It won't hold together, right? I like to use the word explode, but it just won't hold together if every joint is not in equilibrium. So what that means is if we look at this location, if we zoom in on R, what we're going to see is this set of forces. We have here our reaction that we've already calculated, or we can just take from the book because we gave us answers. And when we're zooming in on our microscope, we can see two other forces. We can see QR. Now, we didn't know that QR was going down, and we didn't know PR was going left, but let's think about it. If we know that we have this reaction going up, well, QR, it's the only thing that can to deal with going down. So there's no other member. PR can't balance that force because it's horizontal. So QR is going to have to be going down. But when QR goes down, it also pushes at the same time to the right. So if it's pushing to the right, that means we're going to have to balance it by going to the left. And that's how we get our reactions. So that's how we get our arrows. Now what we're then going to do is we're just going to start by drawing our known force. Our known force is this number here, 293.7. And then I just pick another force, right? What I've done here is I can say, well, I'm going to add QR. Well, QR will have to be going that way, right? And then I take PR, and well, PR is going to close it up. Now, I can also draw it like this, just as well. I can say this is 293.7 and go across. Now, with the arrows, it's important to remember that if I know just one force, once I've created this shape, if I know this is going clockwise, which it is, this is going clockwise, then all of the forces have to be going clockwise. Now, to calculate this value, QR equals, it's the hypotenuse, so it means it has to be bigger. Now, I've written here sine 60, but the reason I've written sine 60 is because that's the trigonometry. So we know that, I'm not going to go into trigonometry, I'm assuming you understand divide by sine 60. I find it way easier just to know sine 60, because so many of the questions we're going to get are going to be 60 and 30 and 45-degree triangles. I find it just much easier to memorize that value and just say, okay, this number is going to be bigger than 293. You're more likely to catch errors if you do that. Now I have here, these are the known values, so we know that if we have a 30-60 triangle, if we start by drawing our triangle like this, we have 2, 2, 2, if we cut that in half, we now have 1, 60, 30, and this is going to be 4, the square root of 4 minus 1, which is the square root of 3. So square root of 3, if we then multiply all those numbers to get 100, if we say this is 100%, well 2 divided by 1 divided by 2 is 50%. So this short side is half the size of the long side. And this long side, the longer of the two non-hypotenuse sides, is 86.6%, or it's root 3 over 2. Root 3 is 1.73 divided by 2 equals 0.866, but if we're using percentages, it's going to be 86.6%. I call it the Disco number because my friend Disco was born in 1986. So, that's how we get these figures. So now we can apply that. We can say, well, if this is 293, we need a number that's bigger than 293. 293.7 divided by 0.866, because I memorized sine 60, gives me 339 units. And because it's going into the node, it's not pulling out of the node. If it's pushing into the node, it's in compression. So compression looks like that. Tension looks like that. I've already started recording the video, which is why I had some stuff written on the board before this video started. And I talked about how I have a script called puns at B, and I make up my own alphabet, and in that alphabet this is the letter for C and this is the letter for T. It looks a bit like the old ancient Japanese for tree, right, the kanji for T. If that helps you. I don't know if it helps you, probably doesn't help you. But once upon a time, that was something I needed to learn. I don't think you really need it for HSC engineering anymore. Okay, so now that we've found 393, well, how do we find this one? Well, we know the relationship between the big side and the small side is 2 to 1. So we can just divide that number by 2, and we're going to get our number of 169 or 170 once we round up. So we can write that there as 170. Where these get harder is when we start dealing with more complex forces. Here we only have 2 unknowns, but what we're going to look at now is we're going to have to figure out where on this diagram we need to go next. So that's where we're going to pick up on part 2. Okay, so I'm continuing on with method of joints for exercise 1.2, and what we just left joint R. We can sometimes call them nodes. We're going to call them joint R. So the terminology in trusses is we call the points where things meet joints, and we call the sticks members. So what we want to look at now is I deliberately didn't do L earlier because I thought it was a little bit more complicated than R, but it's not that much more complicated. Everything we go to from here is going to be more complicated than R. I deliberately chose that as the easiest. Now, what we want to look at is something that has 2 unknowns. If it has 3 unknowns, we won't be able to solve it. So if we look at P, we know this point. Right, I'm going to move the arrow just to help us to see that that is solved. Right, if there's an arrow going in or out, we know it's solved. So we have PR is solved. But PQ, PK, and PL, all 3 of those are unknown. So that's too hard. We can look at L. So L has LK and LP, so it's 2 unknowns. Or we can do Q. I'm going to let my class... So which one do you want to do, L or Q? They're both... Yeah, Q? Okay. So I'm going to get my magnifying glass up here. I'm going to look in at Q and see what's going on there. So, zooming in... what we have is, that's the members of our truss. It's meaning at Q, I'll label the diagram. And we have an external force, 225. Now, we know that these forces have to be in equilibrium. If they're not in equilibrium, then we're going to have a bad time. What would happen is that the joint will pull apart, it will break. So it has to be in equilibrium. Now, we have those members. We have an external force that's in blue, but we have 3 internal forces. We couldn't do this if there were 3 unknowns. So what we're going to do instead is we're going to say, well, this one here, we've already solved. And this is the key to using method of joints, is you have to build on what you've already learnt. So we've said this one here is going into the node. We know it's going into the node because it was in compression last time. So we're going to say that's 339, and we're going into the node. So we now have two unknowns. Well, what we have now is we're going to try and use that same logic when we look at the diagram to say, well, if this is going up and this is going down, we're going to have some difference presumably in vertical and horizontal. We don't know exactly what that is yet. So what I'm going to do is I'm going to break this 339 into its components. So this 339 is made up of 339 is breaking, and we actually, if I take it, left the numbers, it's going to be the numbers we looked at previously. It's going to be 293, I guess, 293 up, and this is going to be across, and it's going to be 170 is what we said. Now, that's just me using trigonometry. Again, we know that this is 60 degrees, so we can break that up. So what we now know is that this force, which could be replaced, is being replaced with a force up. So I'm actually going to remove the red just because it's in components. We're going to replace that into, we're going to break it into its parts. We're instead going to say that what we have is effectively a force up. We're going to actually remove that, remember. We're going to say we have a force up of 293 and a force across of 170. And now we'll see if we can solve it. Well, if we have a force down of 225 and a force up of 293, we don't have equilibrium. So what we're going to do is we're going to use the sum of the forces vertically to solve what that equilibrium would be. So we say the sum of the forces vertically equals 0. Now, we could do the maths, but those of you who've seen me do these things before know I don't really like to do that. I just like to draw pictures. So I say 293 up. Just to help, I'm actually going to use the colours this time around. 293 up. And we have 225 down. And we have some missing amount. And the missing amount is going to be the vertical component of PQ. So I'm going to label this just so we know what's going on here. We have, this is KQ, and this is PQ. So we want to find KQ and PQ. So that's the first thing. As far as KQ is concerned, that's much easier to solve. So let's just, didn't write that down, hold on. 293 minus 225 equals 68. So the vertical component is 68. Now, if we know the vertical component of PQV is of PQ is 68, if that's 68, and this is a 60-degree triangle, if we know the vertical component is 68, we can then use that to determine the whole value, right? So it's going to be bigger because it's the hypotenuse. So what we're going to do is we're going to divide by sin 60. So we get a number that's bigger than, divide by sin 60, which will give us a number. It has to be bigger. Now, for me, that is really useful to think about it in terms of trigonometry, to say we know the number has to be bigger because it's the hypotenuse. It is definitely helpful, and it really speeds up my trigonometry. Divided by sin 60 equals 78.5. That'll do. Now, we said that force is going to have to be going down to bring this into equilibrium. So if it's going down, is that pulling out of the node or pushing into the node? It's pulling out of the node. And if it's pulling out of the node, that means it is in tension. So we can write that in as our answer is 78.5. They just said 90, so we're going to round up, we'll call it 79. Okay. Now, KQ, way easier. No, we have to deal with this vertical component. What is the vertical component of PQ? The vertical component of PQ can be found here. So if we have 78.5, that means this the horizontal component is going to be 39.39. Now, for those of you, Year 11 or Year 12 students who are watching this and thinking, what is going on? Luckily, you don't need to worry very much. Why don't you need to worry very much? Well, because no one uses the method of joints. This is the reason why we tend not to use it. So what I can say now is the sum of the forces horizontally are going to be this. So the sum of the forces horizontally, sum of the forces horizontally equals 0. We use positive. So what we've got here is we've got 170 going this way. That was in green. Trying to make the colours make sense. 170 going this way, and from PQ we have another, let's just label this with an arrow. With PQ, I'm actually going to write the equation if you can believe it. PQH is also pushing in an additional amount, 39.3. So to balance that, we're going to need KQ, which I guess I'll use blue for KQ, to say blue is going to be those two numbers added together, which is like 209.3. Yep, and that's pretty good. I'm happy with that number. Okay, so let's actually write the equation. I normally don't write the equation, but let's do it this time. So we're going to say 0, I'm going to write it here, 0 equals, remember if it's going to the left we write it as positive or negative. Okay, so we're going to say it is minus 170. Why is it minus 170? It's minus 170, that's from here. Actually we're going to write it in letters. We're going to say what we have is QR horizontal minus, and we're saying minus because PQ is also going to the left, like the onset, right? PQH, and then last we have plus, and we're assuming that it's going to have to go this way, right? I'm going to show this arrow in blue just to help us out, right? It's going to have to be equal to KQ. Now KQ, we don't even need to write H because KQ is only in the horizontal. And so we can just fill in those numbers. We say minus 170 minus 39.3 minus KQ equals 0. So what we can rewrite that is we can say, we can cancel out all those minuses. We can say KQ equals 209. I'm just going to call it 209 because we're only, with the trust simulator, we can only get it to a certain degree of accuracy. Now, we said that it was going, that arrow is going into the node. Yeah? It's going into the node, so if it's going into the node, it's compression. So it's going into the node. Okay, 209. Now, when we look at our remaining choices, P only has two unknowns. We now know P and PQ. We only have PK and PL left. So we have two unknowns. So we might go to P next. And that might be how we continue around this truss. So, take my magnifying glass and move this to here. Okay, so we're going to call this P. We're zooming in on P. And what we can see there is we can see Now we already have got some known forces. We already know 79, and we already know 170. So what we have to find is these two unknowns. So, you'll notice the last time I just used some of the forces. I didn't use many diagrams. I probably should have used a diagram, but it can be a bit tough to approach that. So what we're going to look at here is, what we know in this case is that there's a vertical component to PQ. PQ has a vertical component. And only one other member can deal with that vertical component, right? Only PK has that vertical component. So however much up we have from PQ, we're going to have a similar amount down in order to balance it. What that means is we can just get to the point where whatever number we have here, if it's going to be the same amount up, it has to be the same amount down in order to balance this. So what our vector diagram ends up looking like is, I think I did vector diagrams in blue. So we're going to say we're going to go up 79, and then we need to go down that angle. This angle here is getting to 60 degrees. You have to go down by 60 degrees, and then we have a force. Remember, we have to go tip to tail, so we're going to have have another force. I should label these. So what are we calling this one? This one's LP, and this is KP. So this is KP. Once we draw a line down 79, we're then going to have to go across some amount, and the amount that we go across is going to be LP. But the thing is, we have a collinear force here. We have LP, but we also have PR. So what we're going to do is we're actually going to have an amount LP minus, plus or minus PR. So LP plus or minus PR. So if we add those two vectors together. So what that means is if we already know that this is 170, how big, if this is an equilateral triangle, right? We know that this is 60, so this is going to be 60, this is 60, this is 60. So if this is an equilateral triangle, right, let's see if some Year 9 students can tell me what size should this side be?
The same as the others.
Yeah, same as the other, 79. So what we know is that these two numbers added together is going to add us, actually it's just right, plus, is going to equal 79. But we already had 170. Which way was the 170 going? The 170 was going back. It's going backwards. So we have to, remember we have to preserve the rule of tip to tail. So what that means is it needs to go all the way out here and then go back to 170 of PR. Right, so we're going to go all the way out here and then back 170. 170, PR equals 170 in order to get to 79. So how big is LP going to have to be in order for the remainder? LP is going to have to be this long. Right, LP is going to have to be really big. LP is going to have to be 79 plus 170. In order for LP to be big enough, then remember we've got to go tip to tail. So we're going up, down, then LP is going to go all the way across, and then PR is going to bring us back to where we started. Right, so we can close our vector diagram. So it's going to be 170 and yeah, we get 149. Yeah, that's what it should be. 149. Now, LP is it going into the node or out of the node? It is going out of the node. So if it's going out of the node, that means it's in tension. And we can write 149. Now, KP, we figured out KP has to be going into the node. So it's going to be in compression, and it is the same, 79. It's pretty common to get these sorts of shapes. These, especially in Warren trusses, these shapes are really common. We get these a lot. Okay, so now we only have one node, one member left undiscovered. I'm going to just painfully, I'm going to do both L and K, just to prove that we can go from either direction. We could have done L right from the beginning without any information, so we're going to start there. We're going to go back to L and we're going to just treat it. Imagine that we didn't know this 149. We're going to prove that LP, and we're going to find LK that way, and then we're going to do it one more time just from node K. So we're going to move our magnifying glass. Way bigger than it needed to be. Anyway, so this is L. And what do we know about L? Well, L has some forces. L has a force being applied this way, which is 216. It's got a force going up, which is 56.3, and it then has two internal forces that are going to keep this in equilibrium. So we won't take any pre-existing knowledge. Here's what we know. So we have 56 going up. There has to be a force going down to balance that. If there's no force going down, it won't be in equilibrium. So we've got LP and LK. LP and LK. LP only does horizontal. So LP is not going to be able to help us to balance this 56. So what we know is that this force is going to have to be down in order to balance it. LK is going to have to be going down. So if we start drawing our vector diagram, what's it going to look like? Well, we can draw up. We've got up 56.3. And then we're going to go down at this known angle of 60 degrees. Because this is 60 degrees, that means that is 60 degrees. That's alternative angles and parallel lines are equal. And we don't know how long that is, it's just going to be some distance. But we also have a horizontal line, so if we draw this to scale at 56, and we draw that across, we know that we're going to be able to find that up. Now, what we have is we've got to remember we've got to go tip to tail. We have this arrow here that's going a long way the wrong way. So what that means is that LP is going to have to push forward a huge amount and then come back. So let's have a look at how that's going to play out. So what we're going to do is we're going to go up, down, and then here, we know this distance is going to be LP plus 216. That's what this distance is going to be here. This distance here is going to be LP. Well, we're going to write minus just because we typically write some of the forces, some of the forces horizontally to the right as positive. So we're going to say LP minus 216. So it's going to have to be a number bigger than 216. So we go from here. LP is going to go all the way out there. And then 216 is going to bring us back. So I can't even draw it to scale on that diagram. So I'm going to draw it over here. So let's do it again. We're going to go up 56.3 degrees, 3 newtons. Then we're going to go down until we hit where we're horizontal. We're then going to go across. Whatever this value is going to be, this value here is going to be, this value here is going to be LP minus 216. So we're going to go across all the way 216. So if this is 53, it's 100, 200. We draw that to scale. That's how far we go out with that 216. It's actually even further. So because what we need to do is we're going to have to go out here. I'll use that scale now because I'm lazy. That's 216. 216 again. Okay, 216 is going to bring us back to here. Okay. So we're going to go up with this reaction. I'm going to write that in green just to show that it's an external force. We're going to go down LK. Then we're going to go across this amount LP is going to have to go across all the way out here to get us back to here. So this is our starting point. We're going to start here. We're going to go up 56, down LK, across all the way for LP, and then back 216, which is going to bring us back to our endpoint. So our start and end point is the same location. Now that means our 216 is going to be, this value here is going to be LP minus 216. So this value here, what is this value? If we know this value, we can start figuring things out. What is this value? That's terrible again. Okay, so LK, how do we find out LK? Well, it's a 30-60 triangle, so we can just use our sine 60. We know sine 60 is going to apply here. So LK is going to equal, I'm going to use black pen. LK equals 56.3 divided by sine 60, which I'm going to use just in my calculator, 0.866. 56.3 divided by 0.866 equals 65. Okay, if that's 65, this number is going to be half of that value because of this. Again, you can use trigonometry. I'm assuming that most students who started this video are going to switch it off. So if you're still at this point, you're doing well. You're one of the few people who knows how to use method of joints. Okay, so we've gone up 56, down 65, across this big amount, and then back 216 to be here. How much did we go across? Well, LP is going to equal 32.5 plus 216 equals 249. Yay! 249. See, when I was at high school, I actually had a natural talent for maths, but I never actually did any work. Right in year 12, I didn't actually put pen to paper in class at any point. I did exams, and if my friends didn't know how to do a question, I would write with pencil on the table. But I just knew how to do it, right? It wasn't a thing that... All right, 149 there. To go back in the video, that'll be interesting. Anyway, 249 is the right answer because I can see it. It'd be interesting if I got that wrong. But there is a sense of achievement when you're like, hey, I solved this puzzle. It's like getting a Sudoku out, right? It's like, hey, I got it. It worked. Okay, so the last. Okay, so we've also worked out from here. We've worked out that this is going to be going down and 65. Now, what we're going to do is we're going to do the last. Member. We don't actually need to do the last member because we've already solved everything at this point. But we're going to do it anyway, just to show how we could do it from a different direction, and we're just going to do it without that 65. So that would be how you have to, because you can't have two unknowns. Yeah. So hopefully by this point I've scared everyone off method of joints, but. And would say again, there's a good reason why we use method of sections. But okay, we're zooming in on K now. Okay. These are blue because they're components of the force that were given to us. They're not the reactions we calculated. So that's why I'm showing them in blue. Now, what we're trying to find is we're going to find LK Yeah, we're just going to find LK. We're going to assume that we've already picked up this one and this one. So what have we got? We've got 209, 209, and we've got 79. Okay, so how are we going to solve this? Well, it's similar to the other side, where what we're going to have to do first is we're going to have to look at what is the difference in vertical forces. So we can break this 79, we're going to break this 79 into components. So we're going to say that 79 is in fact these forces, and that force, so it's like that diagram, except this force is not actually acting here, it's actually acting up here. So that's why we're going to have 209 from KQ, and then we're also going to have the component from KPH, and this is going to be KPV. So let's break KP into those components. So this is the long side of our triangle. If this is 79, this is going to be 79 divided by 2. $39.5. And this is going to be 86%. So it's going to be 79 times sine 60. So we can write that here as 68.4 and 39.5. Okay, all of our horizontal forces can be summed up as KQ, KPH, and this force here. So, and the horizontal component of LK. We're not even going to worry about horizontal forces for a moment, we're going to focus on vertical forces. What we've said is that we have KP, yeah, we're going to stick with that because it's a little bit simple. Yep, just LP. Okay, so what we're going to have is we're going to draw this diagram. What we have is 125 down, and we have 64 up, 68.4 up, sorry. And we're going to have the vertical component of LK. I'm going to just put LK in green just so that makes it a little bit clearer. So LK is going to be made up of forces like this. So we know the LKV, or as Copeland would probably write that, he'd write that as LK sine 60. It's going to be, I think there's something to be said about doing LKV, but we've already looked at that, we've already broken those components, so at this point, if you just can see the trigonometry, it makes it a little bit easier. So what we can say is LK sine 60 equals, well, it's going to be 125 minus that number. So again, I could use the proper working out, the proper formula, but sometimes drawing a diagram I think makes it a lot easier. The signs are reversed because this is moved sides. So just going to use the black pen for the rest. So what we're going to say is LK equals this 125 minus answer 56.58 divided by 0.866 equals 65 newtons. Now, LK is going up, right? LK has to be going up. If it's going up, it's going into the node. If it's going into the node, it's in compression. And we can see that's the same as what we've got here. Okay. What we then need to do is we also need to figure out, we found LK, which is what we were here to do. We could have gone the other way. We could have used the horizontal instead of the vertical forces. The reason I chose that is because there's already more horizontal forces, and I thought it was confusing. I guess this one last thing I will do, we'll say, okay, let's just write it out. Let's do that. Let's solve it one more time, just by using horizontal forces and see how that goes. So, this is more confusing. So, we're going to write sum of the forces horizontally equals 0, I'm using to the right as positive. So what have I got? I have got 0 equals plus 216.5 minus KQ, that's all of KQ, there's not a component, minus KPH plus, now it has to be plus in order to balance, plus plus LKH. Now, I could here, in this case, say, well, I know that LKH is what fraction of LK. If this is LK, this is LKH, well, we can see, using this diagram, we can see that LKH is half of LK. So we could write that again as saying, I'll write it just again, 216.5 minus 209 minus 39.5, and then we're going to have plus, because it's going this direction. That was our assumption, right? We used this green arrow, we said assume half of LK. Okay, so we can add all this up and move LK over to here. If we move LK over to here, we're going to get a negative. So we're going to say minus half LK, or we'll say LK on 2, equals. So we've got 216.5 minus 209 minus 39.5 equals minus 32. Those minuses cancel out. So that means our answer is positive. Therefore, our assumption was okay. Therefore, it is indeed going to that direction. And so we can say LK equals 32 times 2, multiply both sides, which is going to give us 64. Now, if it's going into the node, which we can see it's going into the node, that makes it compression. Okay, so we solved this side here, LK, we solved that 3 different times. That's how you do method of joints. It has its place, but I think that even when you have to solve the entire truss, that most students I deal with would say they would rather solve the entire truss using the method of joints just multiple times. That, they'd rather just do that all these times rather than using this method. There are some people out there who like it. I like the challenge of it. That said, there's definitely some head scratches. So